Hey guys, so this is just a quick radicals video. So we're going to start with a pretty basic thing, which is just simplifying using radicals. So your goals for this, which are written out in the note sheet, are that you should always get rid of the radicals in the denominator. So here we have a radical in the denominator, and we're going to want to get rid of that. So we're going to have no radicals in the denominator. We're going to want to combine any radicals in the numerator. So if there were an extra root on top, we'd want to combine that into one radical. And then we want to try and have all of our variables in the numerator or denominator. However, as we're about to see, it's okay to have a variable with a larger degree on the bottom as long as it's not a radical, and we'll look at why that's okay. So we're just going to start by rationalizing the denominator. So we're going to start by multiplying by the fourth root, and in order to rationalize the denominator, we want to get this z out, so it's going to be a fourth root, we can't change that, and we always have to multiply by a similar root, so we're going to have to multiply by a fourth root and not a third root or a square root, anything like that. We have to multiply by the fourth root, and we have to make sure that this z cancels out. So we're going to do that by multiplying by z cubed, because if we multiply by that, then their exponents add up to become 4, and then we can get that out of the root. So we have z cubed, and then we have to multiply by 1 officially, so we're going to multiply by the top of that too. Okay, so then this is going to equal, because these both have powers of 4, we're able to combine these, so this is going to equal the fourth root of x to the fifth y cubed z cubed over the fourth root of z to the fourth. So this simplifies pretty nicely. We can pull out this x right here because it's to the fifth power. So we can say x to the fourth root of x, because remember when we're looking at this, we have 5 over 4, because we can pull this out of the 4, equals 1 remainder 1. So in blue here, I'm going to underline this. So this blue is what comes out to the outside. So we divided and we got 1, so that's what comes out to the outside. And then this, what I'm underlining in green, is the exponent on what stays in the inside. So there's an imaginary exponent of 1 on the inside, and y cannot come out because 3 divided by 4 does not give us an integer. So we have y cubed, and then we have z cubed, which we just added, and then we're going to divide that, and then here we have the fourth root of z to the fourth, which is also just z. So as you can see here, we do have a z both in the top and on the bottom, but we're actually going to let that be okay because this z is in a radical. So if it wasn't in a radical, then this would not be okay. We'd have to simplify it more, but because the z on the bottom, the degree is bigger than the z on top, this is actually okay. So now we're going to move on to our next example, which works with simplifying using fractional exponents. So the difference between these examples that I'm about to show you are that these use fractions as their exponents instead of radicals. So if we were to take this y to the 2/3 and change it into radical form, so this is fractional exponent, and this is going to be radical. So if we want to change that into radical, the denominator, so whatever on the bottom, is going to come out and become what our root is, and whatever's on the top is going to go inside. So if we have y squared, but the cube root of that, that's going to be the same as y to the 2/3. So then if we take our next example, which is z to the 5/4, we can make that 4 root z to the 5th, which, as we saw in the last video, 5 divided by 4 also equals 1 remainder 1. So we can make this z to the fourth root of z. Okay, so that was just a quick background on why that works. Okay, now to actually get started with the problem. So for this, we're first going to make sure that all the variables are either in the numerator or denominator, just to start. So we're going to pull this -1 up to the top to become x cubed. We're going to pull this 2/3, and we're going to subtract it from the 3 to become y. And then if we do this, so y to the 3rd minus y to the 2/3, we can also make that y to the 9/3 minus y to the 2/3, which equals y to the 7/3. So we can make that y to the 7/3. And then we want to pull this z actually to the denominator because the denominator is bigger than the numerator, so this is an imaginary 1. So we're going to do z to the 5/4 minus z, which equals z to the 5/4 minus z to the 4/4, which just equals z to the 1/4. And we are going to put that on the bottom, so z to the 1/4. Okay, now at this point, we want to rationalize the denominator, because as we looked at in the last problem, if we have a radical denominator, we need to rationalize it. And this is the same type of problem. This is basically the same as saying the 4th root of z to the power of 1, as we looked at a couple examples. And so in order to rationalize this, in the last problem, we multiplied by the 4th root of z cubed. So in that case, this would be z to the 3/4. So if we multiply by z to the 3/4 over z to the 3/4, we get x cubed, y to the 7/3, z to the 3/4 over z. And again, similar like last time, we note this is okay because even though it says to have all variables in the numerator denominator, it's okay to have a variable with a larger degree on the bottom as long as it's not a fractional exponent, which this is not. So that's good. So we got rid of all of our fractional exponents on the bottom, because remember this act like radicals, so you always want to get rid of those on the bottom, and we're left with that on top. Okay, we're going to move on to our next example. So our next example deals with combining non-similar radicals. So in this case, I actually wrote this wrong. This is not there. So this is actually an imaginary 2 that's here. And so these obviously aren't similar. So you always need to know that if these two aren't similar here, you're not going to be able to combine them easily. It's going to take a further step, which we're going to learn how to do right now. So basically what we're going to do is we're going to combine these into fractional exponents. So we're going to make this 9x squared y to the 1/3 times 3x to the 5th y squared to the 1/2. And now what we really want to do is we want to make these have the same denominator so that we can easily combine these, right? So if we make them have the same denominator, we know that a common multiple of 2 and 3 is 6. So we're going to make sure they both have the same denominator of 6. So I'm just going to do 9x squared y to the 2/6 times 3x to the 5th y squared to the 3/6. So now I can actually combine these. But first what I want to do is I want to make sure that I distribute these top sections into my exponents and integers. So what I'm going to do now is I'm going to say this is 3 squared x squared y, and then I'm going to say this is squared, and then this is to the 1/6. So if you see what I'm doing here, I'm just pulling out a squared and making it to the 1/6 times 3x to the 5th y squared to the 3rd, and then this whole thing is to the 1/6. So now I can really combine these into a huge thing, and I can say that this is 3 to the 4th, because remember I'm just distributing this through, x to the 4th y squared times, you distribute the other one through, times 3 cubed x to the 15th y to the 6th, and that's all to the 1/6, right? So if we're combining these, we can make this all to the 1/6. So now if we really want to combine the whole thing, we can do the 6th root, because that's the same as 1/6, of 3 to the 7th, we're just combining like terms, x to the 19th, and y to the 8th. Okay, so now the good news about this is that we can actually simplify this further. So if we look into how we can pull out certain exponents, I'm just going to draw this in the red over here. So if we look at the 7 and the 6, 7 divided by 6 is 1, remainder 1. So if we look at what I'm underlining in green, that's what's going to be able to be pulled out. So we have 3, and then if we look at here, 19 over 6, so we're seeing what we can pull out of the x to the 19th. This is going to equal 3, remainder 1. So we can pull out an x to the 3rd here. And then if we look at the y to the 8th, 8 over 6 equals 1, remainder 2. So now we can pull out a y here. And then we have our 6th root, so everything else has to stay inside. And now if we look at the purple, what I'm underlining in purple, so these are what's going to go back into the root. So 3, it has 3 to the 7th divided by, or to the 6th root, I guess, has a remainder of 1, which means that this is going to have a remainder of 3 to the power of 1. And then x to the 19th over 6, so we're just looking at the exponents there, also has a remainder of 1, which is going to be x to the power of 1. And then the y has a remainder of 2, so this is going to be y to the power of 2. So this is our final answer. This is what we get. So it looks pretty nice compared to what it was before. I know it doesn't seem great, but this is kind of a complicated way to combine them. It's just always going to be this complicated, and so this is really the easiest way to do it. Okay, so this is another example. I think it's good to have a little bit of practice with this because this can sometimes get super confusing. So we're just going to try this one. This one is pretty messy because there's a 7 and a 4, but I think it's just good practice. So first we're just going to combine change the terms, and we're going to make them fractional exponents. So just like we did in the last one. And now again, we want to find the common multiple of these. So that's going to be 28 so that we can combine the fractions. So now we're going to change this. And this is going to be 4 28ths. And this one's going to be 7 28ths. So now, again, like we did in the last one, we do have to distribute in. So we have to make it 2xy to the 4th to the 1/28th, right? Because we're just distributing the 4 in, times, and then in this case, we're actually going to make it 2 to the 3rd, x to the 3rd, y squared, to the 7th, to the 1/28th. And then we're going to distribute the 4 and the 7 into these. So we're going to make it 2 to the 4th, x to the 4th, y to the 4th, times 2 to the 21st, x to the 21st, y to the 14th, and you can see why I said it gets a little messy. This is all to the 1/28. So now if you look at our final answer, where we're going to do a 28th root, so obviously a little unrealistic in what would actually happen, but it's going to be a 28th root, and we're going to combine all of our like terms. So remember, we always have to add the exponents, so it's going to be 2 to the 25th, x to the 25th, y to the 18th. And unfortunately, we can't pull anything out because 25 divided by 18 is going to be less than 1. Again, 25, and same with 18. So if any of these were bigger, let's say it was 29, then we can pull out the 29, and we could pull out the bottom part of the 29, but it's not, so we can't pull out anything. So this is going to be our final answer. We're going to leave it at this. Okay, and then moving on to our final step, we're going to be working with conjugates. Okay, so if you have a radical like this, or a fraction like this with radicals in it, you still want to get rid of the radicals in the denominator. But you can't easily do that because when something is combined with addition, it makes it a lot harder to just get rid of the radicals. So we are going to have to multiply by a conjugate. So if you remember from some of the last units, when we multiply a conjugate, these two are conjugates. So obviously the variables on the left and right are the same, but the sign in the middle are different. And this is so that when we multiply them out, it becomes x squared plus xy minus xy minus y squared. So then these two terms in the middle cancel out, and then we're just left with x squared minus y squared. So basically when you have radicals, that means that the radicals are going to cancel out, and you're going to be only left with non-radicals, so variables or integers on the bottom, which is really nice for what we want to do. So when we look at a conjugate, we're going to be looking at the conjugate of the denominator. So conjugate of denom. So if we want to look at the conjugate, we need to have the x and the y. So this is essentially x and y. So we're going to keep those the same, 2 root 3 and root 7. But instead of keeping this plus sign here, we're going to make a minus sign. So this is our conjugate of the denominator. So this is what we're going to be multiplying by. And when we multiply by it, you'll see it's going to simplify out really nicely. So I'm just going to rewrite this. 2 root 3 minus root 7 over 2 root 3 plus root 7. And we're going to multiply by 2 root 3 minus root 7 over 2 root 3 minus root 7. And so when we're going to start with the denominator because it works out pretty nicely. So when you multiply these together, we get that it's 2 root 3 squared, which becomes 4 times 3, because when we have roots multiplying together, those cancel out. Because if we have root 3 times root 3, that becomes root 9, which is just 3. So obviously the radicals cancel out in that case. So it's 4 times 3, and then we have minus 2 root 21 plus 2 root 21 minus 7, because again, the radicals are going to cancel out when you multiply by the same thing on the inside. And so these terms actually cancel out. So then you're just left with 4 times 3 minus 7. So we'll simplify that in a minute. And on top, this is a little bit more messy, but it's the same thing to start with. 4 times 3 minus 2 root 21 minus again 2 root 21. And then there are two minuses here. This is actually going to be plus 7. So then if we start simplifying that, we can see that's 12 minus 4 root 21 plus 7 over 12 minus 7. So if we take our last step and simplify it, we get 19 minus 4 root 21 over 5. So that is going to be our final answer. So when you're working with these, always just remember to multiply by the conjugate on the bottom, and then the same thing on the top, obviously. And the bottoms will cancel out. You never want to have a radical on the bottom. So if it cancels out to something like this, that is good. Leave it at that. And the top, that's okay to have radicals in it, obviously. And so, yeah. Also, on the test, if you have something with just integers and you do have a calculator, I think it's always a good idea just to throw this in your calculator right here, and then throw this last thing in your calculator right here, and make sure they get the same answer. I would always do that when checking your answers. And even if they don't, let's say that one of these is the x instead, you could even set a variable to x, so x equals 2, y equals 3, and plug that in both this step and this step and see if you get the same thing, because I think that's always a good thing to do just to check your answer. So I hope this was helpful. I know your test is soon, so good luck.